Today, we're going to tackle a slightly more challenging topic. Um, so, we're going to talk about my research into CPU driven LLM or agent training. I'm sorry, I said that all wrong. CPU driven AI training, um, or at least how you would begin to approach, I think, an NLP system. And to be clear, a lot of my research in this space kind of went between. So you have this ladder basically. So you start with something called SVD, which is I believe it's a scalable vector decomposition, and we can go look this up. Let me go. What is singular value decomposition? My apologies. So singular value decomposition, if we looked at images, it would sort of give us this idea that you're taking a matrix rather, and you're going to basically compress it. And so this is kind of this is like one of the fundamental moving parts of how we get into the world of modern LLMs. Where I sort of then go, and I believe truly that this is where the research goes. So you go from an SVD, which again is matrix based, and it's all about how do you find the features in a set, and then you go to BERT, and BERT actually, regardless of what this thing says, BERT should do what's called encoding and decoding. And I'm going to name this topic a little bit, but in general, the decoder is what we see in GPT, where you're sort of printing what the next character in a set would be, versus encoding would be sort of, classifying a piece of incoming text. And so BERT should be doing actually both. So you can see it here. It uses transfer learning to continue learning from its existing data when adding specific tasks and layers. Although that's also really not quite what we want to explain. And yeah, so you can see on this example, here, let's open this in a new image tab so you can see a little better. So this is sort of an example of how encoding is that you're going to take this input string, help Prince Mayuko transfer huge inheritance, and BERT is going to classify it, which is basically, it's going to classify it as either spam or not spam. So that's classic encoding. And so, it tends to be, when you go look up deep learning, a lot of the times what you're going to get in deep learning, let's see, what we want class. Yeah, here's another chart where, basically you'll often find this as soon as you start looking into machine learning. So it's this idea that different algorithms will classify data. And so BERT is just a sort of a way in which you can take this sort of this featured learning that is inherent in SVD, which basically is just compressing data. It's basically mathematically culling out anything that's not relevant in the data set, in terms of it's basically a mathematical way to say, hey, this doesn't really tell us anything interesting about the data, so we'll compress it into this column. We'll group everything together here, so we can take 100,000 columns, and we can turn it into 1,000 columns. And so, but what each column is going to sort of show is actually a much more interesting feature. And so that's kind of it's aligned with this idea of classification, which also going to BERT, same idea as this chart right here on the left of classification might as well be that on one side of the line is spam and one side of the line is not spam. Of course, you could probably have a data set that has multiple different neighborhoods as well. I don't think it has to just be a line through the middle. You could probably have the same classifier kind of operate on different areas of data, and maybe, would draw a circle around the data, for example, instead of just lined through it. That's all within the realm of possibility. And so, like, this was kind of the studying that I was doing 2 years ago. So it just has a GPT to print out, like, you give us a ladder of concepts to go from, like, your most basic building blocks to up to GPT. And so you can see this top line here, same kind of concept that I introduced. It's you're reducing sparse representation. So you're taking that 100,000 rows and you're reducing it to a smaller space. Of course, what I asked was, how do we go from like this basic SVD concept all the way to GPT? And then this would be kind of the next concept I'd pull out. So it's second sort of stepping stone. It sort of says that we're going to predict nearby words. And so this is what BERT kind of mostly claims that it does, which we'll go look at in a second. But it's this idea that, so think about what GPT does, or what people say that GPT does, is all it's doing is predicting what the next token is going to be. And so I don't even want to answer how GPT would operate on an image. But at the end of the day, you could represent an image into, this sort of quote unquote latent space, and do decoding on it. So for sequence models, and this is saying pre-transformer deep learning, I think, we're not even going to cover this one because it says it was, it's hard to scale, and that's my understanding of these data structures. So for like, this is an RNN is a recurrent neural network, and it's not. Yeah, I think the whole idea of attention was that I think with an RNN, we'll go clarify this in a second, but the idea is that you have to go update every single node in the network, versus an attention is this idea right here, is that you're going to selectively focus on relevant tokens. You're not going to go talk to every single node in the network. So it's like, rather than be like an n factorial problem, we'll go double check that in a second. You're selectively focusing on what's relevant in the network. So then once we get to transformers, it says right here, replaces recurrence entirely with attention. So it's basically, again, it's selective updates to the network. And then going to BERT is bidirectional, meaning that it does both encoding and decoding, versus GPT is meant just for decoding. And then the core thing that we'll focus on here is this idea of masked language modeling. And I probably did a poor job in this video, but I'll probably, I'll get to the point of kind of why all of this is important in a second. And then just to be thorough, masking the LLM. And by the way, like, this is how I do. And I think for anybody that would think that this is a poor choice to do your AI research using AI, I mean, I think that's the most meta and awesome thing. So it answers to us that, in fact, RNNs, it's not n factorial, but it's actually more of a problem that you can't parallelize it, which is kind of an interesting thing. So it's basically saying right here, you can't parallelize tokens. You have to compute everything in order. So I guess it's basically saying, which I'm guessing it's combinatorial, meaning that, like, the order in which you process the dependent, like, for instance, it has here H1 goes into H2, like, you would probably, the processing H2 requires you to first process H1 is probably the issue. And then to clarify further, so BERT does not do decoding. It just does encoding. And it's possible, as I was researching, I was just looking at the encoding problem. And then we'll go look, like it says right here. So it does say, and this is maybe the nuance of why I was thinking it does decoding, because it does predict tokens, but it does so like with a quote unquote, it says MLM mask. I don't know what the it says MLM task, but it basically, it does training by basically, just like you see in the synthetic data, talks about, trying to give AI more data to train on. It's this idea that you're going to kind of remove a word from a sentence, and BERT is all about like how can you predict what that kind of removed word is, if that makes sense. And so by doing that, you kind of give yourself an arbitrarily large amount. You already know what the answer is because you've taken like a real piece of text. And what you're trying to do is you're trying to basically generalize, like, can you always understand what context the meaning of a word might have by being able to predict like a masked word in such a way. And then I guess the encoder versus decoder question, because it gives us the distinction right here. It's more of a subtle architecture question, because here it does do output, but it's just more of a quote fill in the blank versus the GPT is the. So it says it here. It's like it's bidirectional. You could go in either direction versus GPT is left to right. It's token by token. So right, and so BERT is less efficient because it's more about understanding what the code base is doing. I'm not sorry, not the code base, but the actual sentence is doing. And so next we're going to prompt. It actually GPT remembered that I had researched this with it, so it's basically saying next, let's like compare and contrast the method that you had put together. All right, so this is where it's going to get kind of. And by the way, we have a whole chart that's going to. It's not. We're not just. This is the chart that we're kind of working up to. So it's this idea that I had been exploring that, can you basically do AI training on the CPU? And, basically here, at the risk of AI just being completely sycophantic, I was exploring, can you kind of combine the concept of something called n-grams, co-occurrence, distance, clustering, and then traversal ideas into just a SQL table and produce something that's remotely similar to kind of all of these learnings packed into like, the SVD to RNN to BERT to GPT relationship that we just studied. And what's wild to me is that, but this is where it's going to get more wild, I promise. So basically it says that you almost already have attention just by way of doing n-grams, co-occurrence, weights, frequency, and it's saying that for each query term, traverse the co-occurrence graph. So that means like if the word bear co-occurs with hiking, and then you could like I also explored topics where you could explode out like the word bear. You could swap in other animals, so you could have a topic graph. You could explode out the word hiking with other, again with other similar terms. And you could build relationships and you could study co-occurrence that way. And it's sort of saying that, there's already a compression in doing so. Versus, let's see. And I think we're going to kick out of like the sort of the GPT, deep dive that we're doing here in a second, but you can sort of see like what I'm pushing the LLM to do. I was pushing a year ago to see if we could do CPU-driven AI training or CPU-driven AI equivalent of what we have with GPT. And the main thing that I had posted about a year ago was this idea of can you, and you can see here, like a year ago, can you build a neural net based on jump statements versus mul? And the idea of that is that a GPU is very good at mul being multiply, and mul being more specifically related to this original concept of, I'm trying to find our original matrix diagram here. So mul being very relevant to, these whole matricey types of computations. And so my research was into like, could we basically drive everything just using a SQL database? And this is kind of whatever we're looking at on screen is kind of the extension of that. What's wild is that AI will be so sycophantic, it'll be like you can win against Transformers on such and such and such. But this is where I want to and I'm taking 15 minutes to get there, so I probably need to improve my information delivery on these complex topics. But the general idea here is that back a year ago, I had gone and covered the fact that this guy wrote a paper, and so. And this is where it's going to get wild. So he wrote this paper, Slide in Defense of Smart Algorithms for Hardware Acceleration for Large-Scale Deep Learning. And this is all about show that training in Slide on a 44-core CPU, here, we'll make this bigger, is 3.5 times faster than the same network trained using, this is TensorFlow, on a Tesla V100 at any given accuracy level. On the same CPU hardware, Slide is over 10 times faster than TensorFlow. Now, what's crazy about this is that basically this guy, his name is Srivastava. So Srivastava, basically, he's now at fucking Meta. And he's a principal at the Superintelligence Labs. So in the short time of a year, he had published this. I don't know if there's a date on this paper. Says March 2020. I think he then raised money to go build this thing. This was Third AI Corp. And he got acquired by ServiceNow. So he was working on CPU-driven training. And right here, production-ready Gen AI on CPUs. So for those of you who actually watched and waited or wanted to, have that patience, this is kind of what I was driving toward. So right here, semantic search index, data preprocessing, named entity recognition. But it's this idea that you really don't need a GPU. And then this chart, I think, kind of captures, I just asked it to kind of condense all of the research that I've been doing into like a chart, which is kind of, I think, my new favorite technique. I've been working on a database of job descriptions in particular, and I've seen how I could extend it. All this stuff in this layer up top left here is like all pretty standard. Ngram directory, pretty standard. And then this is where it gets kind of interesting. So it's basically kind of likening like this, the fact that the GPT put this section into a matrix like looking thing. It's pretty SVD like. You can see it even says sparse matrix. And then you go through a clustering pipeline to try to this in the case of jobs, like you'd understand, for instance, like that maybe like let's say a sales job co-occurs with like a Salesforce database or something like this. And then the synonym expansion layer is this idea that like how do you like relate, if for instance you have all this co-occurrence of, let's say, you could do two directions. So synonym co-expansion would be this idea that you're going to go horizontal. You're going to say, so Salesforce is like HubSpot. And not even per se, like you might just use a dictionary. You might use a dictionary. You might use like a technology graph. So it's more horizontal swapping. So Salesforce, HubSpot, Zendesk, maybe all would kind of go together, for example. These are all CRMs. You could also go vertical. And so you could say like CRM is more general than Salesforce. And that, CRM design is more specific than Salesforce. Or I'm trying to think of a concept within like the realm of CRM, but maybe I think like a technology in Salesforce would be like Lightning Pages. Should be like a technology in Salesforce. So that would be going vertical. And so you'd have this idea of sort of saying like, you could then expand out every record of a job to sort of say that, here we'll make this part because we're looking at this right side now. But you could basically say that, and you can see it right here, example expansion, cloud becomes cloud computing, AWS, Azure, blah, blah, blah. And so that's kind of saying that like you're going to explode out your data storage and say like, okay, we could store all of these records in the database. So anytime a query comes in, you're going to match, any one of these. Or if you're trying to cluster, likewise, like you're safely kind of saying that these jobs are all the same. Let's see. And so then it goes into the query interface down here. And so the idea would be a user comes in and says, I'm looking for cloud backend engineer with AWS experience. It's going to tokenize it. So it's going to get all these like, token keywords. And remember, we're exploding out the database into its many synonyms and so forth. And again, this is all in SQL. And then we're going to expand out these keywords with synonyms. So we're going to basically take one keyword and turn it into like 20 or 100. Or once you do combinatorial stuff, like maybe it's 1,000. So the issue is kind of that like you're going to blow out your storage. Whereas like when we look at the matrix-based methods, it's all about condensing. But what you gain is understandability of a system. And so then here it's saying, we're going to do cluster profiles. So this is the clustering step. And then we're going to score and rank and then return results. But the idea is that you always in these systems, you have to kind of understand like both with databases, like it would be a parallel. You have to understand what's your write time and your write time complexity versus your read time. And so the idea, I think the way this system gets designed is that to write all of this is not that expensive. The main issue is the synonym expansion layer, because you're gonna quickly blow out your database, meaning you're gonna have a huge amount of storage on not a lot of data, and you're not per se doing compression, meaning you're not pulling away data. And I don't have it fully researched of like, do you actually need all of the original like verbosity in order to continue training? And the answer is that you might. And like you have to keep in mind too that when these like giant GPU farms are training data, it's a huge amount of compute. But on the query side, it's like it really should just be mostly like you could boil away most of the irrelevant clusters, because clustering by nature of it, I have to go back and look at my research into this, but like I always tend to prefer this idea of variable clustering. So sometimes clusters are like static, like once you build the cluster, you're done. But the technique that I like is called like hierarchical clustering. Hierarchical agglomerative clustering. Sorry, you look this up. Hierarchical agglomerative clustering. All right, so this is kind of what that looks like. And it's this idea that you could cluster at any stage that you like. You could cluster by saying that you want to cluster at the layer of CRMs and customer support software and payment software. That's a pretty general idea. Or you could cluster within like CRM land and talk about like field mapping. You could talk about like auto trigger actions. And that would be kind of a different layer of that hierarchical cluster. Let's try to find another example. So you can see in this chart here, this is kind of not a great example because its examples are very abstract. Let's go find a better one. Here, this is the example I believe that I had used, but it's just not a very good image. Let's go pull this open. And let's pull this. Yeah. Okay, cool. So you can see here, like you can cluster and sort of say animals at the top. You could drill into that and talk about just vertebrates. You could drill into that and talk about birds. You could drill into that or talk about mammals. Or you could talk about the individual members within those families, if that makes sense. And so let's go back to our chart. Let's go look at this bottom. Yeah, and so like why is this type of approach good? It's because it's explainable. Because of that hierarchical clustering method that I just mentioned, you could customize, how you want to adjust like known clusters in the system. Even though this says it's efficient, I don't really. I mean, maybe compared to like training huge GPU farms, it's efficient. I don't per se think, but it's definitely, to be clear, like this system is not, like this proposed idea is not basically anywhere close to what you would get out of a transformer, but it's this idea of, it's still pretty powerful. Here, and it even says it right here, like how does this compare to BERT? And so it's this idea of how does this compare to dense embeddings? And it's saying here it's learned automatically versus this is like, I don't even think this is heuristics, but yeah, this is much larger storage versus this is compact. Is kind of the main trade-off of this. But the idea, the more interesting thing is, again, the fact that, this guy who had proposed all of this research in this space, was not only acquired, but he now works at the Superintelligence Lab. So I think that sort of demonstrates to you, what the heck is Muse Spark? Let's go check that out. Scaling toward personal superintelligence. Well, this is a pretty incredible find. So check this out. So this was released 20 days ago, and they're kind of claiming that this benchmark, we'll pop this open full screen, but that it beats, I mean, this is obviously classic, right? But it's saying that it beats every single existing model. I mean, I think at the time, Opus 4.7 had not dropped. But it's saying that it beats basically everything, which is kind of interesting. Okay, let's keep going. Held out code-based perplexity. Compute savings. So it seems like they're approaching like just a fundamentally different way, because they're kind of comparing it to DeepSeek and Kimi, which have usually, it seems like, for at least DeepSeek has different techniques than the foundational models that we're getting out of these AI labs. Which sounds interesting. Like we're going to hear more about this stuff soon. This chart doesn't make any sense, but bioweapons refusal, that's good. Yeah, I think I wanted to just cover, this idea that, you shouldn't be afraid of trying to understand or research AI using AI. And you don't obviously have to go so deep. And some of the reasons that I went into this in the first place was that I've kind of been dancing around topics in AI for probably over 10 years. And when GPTs came around, I had to take the knowledge that I had and sort of, I remember 10 years ago, I'd hang out in these like deep learning communities, and I'd always walk away thinking like, you could just do this in SQL. And then a lot of the times, like the way that you learn anything in a deep way, whether it's in academia or whether that's being like deep in the engineering department, is you kind of have a question or an hypothesis, and then you just follow it, and then you try to map it to what other people are doing. And it's often a great way of learning, because not only are you kind of taking your own original thought and you're dancing around the ecosystem, but you're also learning as you go, like what other people in the space are doing. And you're able to build concepts that way. And so even though, like, you're not producing the type of AI magic that we see with GPTs in these methods, like, where it could fit and be useful. And not to say, like, I mean, maybe this guy had already kind of cracked the nut on, whatever he was doing with CPUs. And the core idea is that there's just different architectural differences and different, if you could get things working on a CPU, it opens up a massive amount of opportunities, because there's a lot more abundant CPU compute than there is GPU. But the idea is that, yeah, like, even if you could unlock the CPU for some elements of, let's say, information retrieval, or just some elements of what you would maybe hand off to an LLM today, not only could you get more determinism, you could get more explainability, but you'd shave down cost. Is the main thing. Is really shaving down cost. So I just wanted to share that research that I had been doing, because I think it's interesting. But I think the more noteworthy thing is that my research led me to sort of show that not only, like, did this guy have this paper that built this third AI that received funding, but then he himself now works at the Superintelligence Lab, those are strong indicators that whatever he was onto is highly valued, basically.